Okay, so we're going to finish off Chapter 8 with random variables, probability distributions, and expected value. So, we will do, in this video, definitions, a game example, which will include what is meant by a fair game, and then a raffle example, and a business decision example. Business decision example. Boink. And so most problems are like this. So problems 1 and 2, 5 through 15, 17 and 20, 23 and 24. Which are the raffle ones? Oh yeah, 23 and 24, and 35 and 36. Some of the calculations of probability in these can be a little bit difficult, but the expectation value calculations are pretty straightforward. And then the raffle problems are problems 27 through 30, and then 39 and 40 are business decision examples. So these are problems from 8.3. So we'll start with some definitions. Oops. I put in my examples typewritten, so I'm going to need to insert a little bit of space here to be able to talk about the definitions a little bit. So definitions. There we go. So what we're doing is we have a bunch of events. They have different probabilities of happening. So we need a couple definitions. First off is a random variable gives a number to each event. Right? So a bunch of different stuff can happen, and we say, okay, well, we'll give each one a number. Often this is a payout, right? So if you win, you get this amount of money. If you lose, you get that amount of money. So for example, if you roll 2 dice, right, assigning the sum of the dice, the numbers on the dice, is a random variable. Oops, to each outcome, sorry about that. To each outcome is a random variable. So, to the outcome 1 on the first die, 1 on the second die, you assign the number 2. To this outcomes 2 and 1 and 1 and 2, you assign the number 3. Right? And then you can do that for all of them if you wanted. And then each assignment, we can call this x1. X is the traditional letter. x2, we can say the probability of x1 is 1 out of 36. Probability of x2 is 2 out of 36, etc. So for each outcome, we give it a number, and for each of these numbers, you give it a particular probability. Right? And this is called a probability distribution. And the whole process of assigning a number to an outcome is called a random variable. Really what a random variable is a function. To each outcome, you give it, to each input, which is each possible event, you give it a number of some sort, except it's called a random variable because that's what it's always been called. Okay, great. So, now, here's our example 1. Here's a game. Right? And the game is, you and a friend sit with a deck of cards, and a card is picked at random and replaced. And you just play this over and over again. If the card is a spade or a king, your friend pays you $2. If not, you pay your friend $1. Should you play this game? And of course, the question that's sort of being asked here about should you play this game is, will you make money if you do this? So, what are the outcomes? Well, there's two outcomes. You can win or lose. Right? You win $2, or you lose $1, depending on what you pick. So we can set up our little probability table by saying that here's the little table. My first row will be my outcomes. You win $2 or you lose $1. And we'll call this one x1, that's my first outcome, x2 is my second outcome. So, what's my random variable, RV, for random variable? Well, what's the number that I want to assign to this particular outcome? 2, because I'm winning $2. And the number I assigned for this particular outcome is -1, because I am actually going to lose some dollars. And then I want to know what the probability of my outcomes are, so xi. So probability of x1, what's the probability of winning? Well, that's the probability of getting a king or spade, and we know what that is. That's 14 spades plus 4 kings minus 1 king of spades over 52. So the probability of winning is 17 over 52. 18 minus 1. No. I knew there was something wrong with that. There's 13 spades. So it's 16 over 52. Okay, good. And that's 0.3077. Oops. Now what's the probability of losing? Well, we don't actually have to calculate the probability of losing directly. We know that it's 1 minus 0.3077 because it's a complement, and that's 0.6923. So 0.3077, 0.6923. This part is what the book uses, just the random variable and the probabilities. That's what they call a probability distribution. I like to have a little row at the top to say, okay, well, what are my outcomes? And I also like to put a little row at the bottom where I multiply this, the random variable, times the probability of that. And if we do that, we get, what do we get? 0.6154, because that's 2 times this, and then we get minus 1 times 0.6923, which is minus 0.6923, and then a little box at the side. This is the sum. This plus this is minus 0.0769. That's the expectation value of this game. Great, so that's what the expectation value is. You take your random variable, you multiply by its corresponding probability, you get some number, you do that for the other outcome, you get another number, here's a negative one, add them together, that gives the expectation value. What does that mean? What does expectation value mean? And what it means is it's how much you would win or lose in this case you'd be losing money on average each time you play this game. Right? And that's a little bit tricky to think about, right? Because every time you play the game, you either win $2 or you lose $1. So why is this minus 0.0769? Actually, this is measured in dollars, so this is about 0.8 cents. This is about 8 cents. You're losing 8 cents each time you play that game. Well, the average part is really important, right? Because suppose you played 10,000 times. We can do sort of the same calculation. how much would you win or lose? Right? So we set up the same table. Outcome 1 is you win $2. Outcome 2 is you lose $1. How many times you won or lost? Well, if you're winning, oh, that's not right. This is my random variable, right? $2 minus 1, right? So, how many times goes in the next row? Right? If you play 10,000 times and you win this percent of the time, well, you win 3,077 times. And you lose 6,923 times. Right? So 10,000 times 0.0377, that tells you how many times you'd win or lose. Great. So, what are your winnings? Or losings, I guess. Losses. Well, if you win $2 every time you play, and you play every time you win, and you win 3,077 times, you win $6,154. If you lose $1 each time you lose, and you lose 6,923 times, you lose 6,923, right? 2 times 3,077 is 6,154, minus 1 times 6,923 is minus 6,923. So what's your total? Minus 769. After 10,000 games, you are down $769. You've lost $769, right? And you can see how that works out, right? Every time you win $2, you get this much, but every time you lose, you lose $1. You go up some, you go down some, you tend to go down more than you go up, and you end up at 769. So, on average, in each game, you lost, well, minus 769 over 10,000, minus 0.0769. And that's our expectation value. And that's what expectation value is. It's how much would you lose on average if you did it over and over again, right? So you do it 1,000 times, you see how much you would lose, and you divide it by 1,000, that tells you how much you would lose. You wouldn't want to play this game in the long run because you would lose money, right? And that's how casinos, for example, make money. You might want to play it, for 10 times because you might actually win because it's in the short run, but in the long run it's a little bit tricky. So I need a little bit more space. So we're going to insert some space here because we're going to introduce the idea of a fair game. So how much would you have to win for the game to be fair? What does it mean to be fair? Fair, the expectation value equals 0. Right? And what that means is that in a fair game, over the long run, you're not expected to win any money, but you're not expected to lose any money. Right? And so, there's no determinate way that the money is flowing. In the first example, the money is always flowing to your friend. Here, it doesn't flow to you or to your friend. So let's set up our table again. And again, outcome. You can win $2. You can lose $1. Right? Random variable. We'll give those numbers minus 2 and 1. Probabilities. Oops. We want to change that. Probabilities are the same. 0.3077. Because you still have the same probabilities of winning and losing. And then 0.6923. Okay. And then the product. Again, in dealing with the book or with Math Excel, this 2 rows, that's what they usually give you. That's the probability distribution. I like to have a little explanatory thing on the top and the bottom and have my expectation value here. Right, so I multiply down and then I add across. Now, if we want the expectation value to be 0, right, what do I have to make this number? And I'll call that z. So what does z have to be so the expectation value is 0? Well, the table is set up so you multiply down, so 0.3077z, and then you get minus 0.6923. We want these two to add up to 0, so you get z equals 0.6923 over 0.3077, which is about 2.25, I believe. Right? So if each time you won, instead of winning $2, you won 2 1/4, then the game would be fair, and if you and your friend played it over 10,000 times, you would expect not to win anything, but not to lose anything. Of course, if you play for 10 times, you might go on a winning streak and win a bunch, right? I mean, expectation value talks about what happens in the long run, not necessarily in a very short period of time, right? If you played it just once, either you go up 2 or you go down 1. If you, I suppose that should just be win. If you played a bunch of times, though, the expectation value dominates. Okay, so that's a particular example. Here's another example. It's really the same setup. A raffle sells 1,000 tickets at $1 each. There's just a couple things to keep in mind here. Right? So what are the possible outcomes? X1 is you win $100. That's the grand prize. X2, second possible outcome, you can win $50. X3, third possible outcome, you can win $10. And there is, although it's not stated, a fourth possible outcome, and you have to keep this in mind in these sort of raffle problems, where you win nothing. In fact, most tickets win nothing, right? There's 1, 3, 8 total prizes out of 1,000, so most of them will lose. Okay, so then we set up our table, right? What is the random variable? Right? What number should we assign to this? Well, how much do you actually win? You win $100, but you had to buy a ticket at $1. So your net gain is $99. Your net gain here is $49. We don't need a dollar sign. And your net gain here is $9. And if you buy a ticket and you don't win anything, then you lost $1, -1. And what's the probability of these things? The probability of winning is 1 in 1,000. The probability of winning $50, well, there's 2 prizes of that, so that's 2 in 1,000. Probability of winning $10, there's 5 of those, so that's 5 in 1,000. Probability of losing, well, there's only 8 winning tickets, so there's 992 out of 1,000 losing tickets. And again, this part is the probability distribution, an assignment to each possible random value, this random variable, this, and this, a particular probability. And we multiply them together, so this becomes 99 out of 1,000, 98 out of 1,000, 49 times 2, 9 times 5 is 45 out of 1,000, and then -1 1,000. So that's in calculating the expected value. Once you have the table for your random variable, multiply down, and then you add up across. So if you add all these together, you end up with -750 over 1,000. So there's my expected value, -0.75. Right? So if you played this lottery, this raffle over and over again. If you go to the same little fair every year and you buy a raffle ticket, over the course of your lifetime, you'd expect to lose 75 cents each time you played. So if you played, for 50 years, you'd lose, well, if you played for 100 years, you'd lose $75. I guess 50 years would be 37.5. And, if it's for a good cause, you might want to do that. So one of the things about expected value, it tells you about what happens in the long run. It doesn't tell you about what happens in the short run. So if you're making decisions based on on expectation value, you might have to take other things into account. And we'll see that in this particular example. So a company is making a decision. They want to start a research program. It costs $1 million up front. If the project succeeds, and there's a 60% chance that'll happen, then they'll make $1.5 million in revenue, right? So there'll be a net profit of $500,000. If the project fails, they can then, try a secondary project, right? If the secondary project succeeds, and there's a 35% chance of that, then they'll make $750,000. They'll be down $250,000. If the secondary project fails, well, then they have to junk the whole program and they sell the equipment for $10,000. So should they try that, right? And we can set this up as an expectation value problem. And so what are the things we need to do expectation value? We need to know what the outcomes are, and we need to know what are the numbers we want to assign to each outcome, and we want to know what the probabilities are. So outcomes, we say S1 is the primary program succeeds. That's one possibility. S2 is the primary one failed, but the secondary program succeeds. And then F2, secondary program fails. So those are really the three outcomes. Either the first thing works or it doesn't, and if it doesn't, then either the second thing works or it fails. And our profit here is $500,000 if the first one succeeds. Right? A profit, we have a negative profit for the secondary one of minus $250,000. And if the secondary one fails, then our profit is actually minus $990,000. We invested $1 million, and if everything fails, we can sell it off for 10. So we lose minus $990,000. Okay, so there's our outcomes. There's the numbers that we will, this will be a random variable, teach outcome. And what we need is to know, well, what's the probabilities of these things happening. So we need probabilities. And to do that, we will set up a probability tree. So we can have the first project can succeed, which it does 60% of the time, or it can fail, which it does 40% of the time. If it fails, then we have a secondary chance of a secondary project, which is 35%, so S2, and that's 35%, and then it can also fail. And if it succeeds 35% of the time, then it fails 65% of the time. And so there's our various outcomes. Probability of this outcome is 0.60. Probability of getting success on the second one, we have to multiply these two together. 0.4 times 0.35, which is 0.14. And the probability here is 0.4 times 0.65, and that's 0.26. And notice that these three add up to 100% because something has to happen. And these two, right, 0.26 plus 0.14, that's our 40% of failing, right? So these add up to 0.4. So now we can actually set up the expectation value box. So outcome, S1, S2, F2. The net, our random variable, 500,000 in profit, minus $250,000 in profit, and minus $990,000 in profit. What's the probabilities? 0.6, 0.14, we calculate that here, and then 0.26. Great, so to find the expectation value, Multiply down. This times this is 300,000. This times this is minus 35,000. This times this is minus 257,400. And we'll put all this in a big box, in a table. Right? 3 outcomes, 3 numbers assigned to each outcome, 3 probabilities, and multiply it down. And then what's our expectation value? Calculate the expectation value by adding these 3 numbers up, and it's 7,600. And this raises an interesting question, right? The expectation value is 7,600. So should you do it or not as a business manager? Well, there's a couple different things to think about here, right? One is if you're in a big company like Target or something, you might get 10 people coming to you with essentially this data, saying, well, here's our analysis of what's going on. Do you want to fund it or not? Well, if you have 10 different things going on, then, there's a big enough chance that the expectation value is actually relevant. You'd say, well, 10 of them, some of them will work, some of them won't, but on average we should make about $7,600 on each one, so on average we'll make $76,000 if you fund 10 of these, right? And so you can say, well, sure, we'll go with that. Some of them will work, some of them won't, but on average we'll make money. We'll make $76,000. On the other hand, you might look at that and say, well, we're investing $10 million to get $76,000 in profit. There's a better way to use our money. So maybe even though the expectation value is positive, you might decide that the return is actually very small. On the other hand, if you are, a small company and you're just going to fund one of these things and you look at these numbers and you say, okay, should we fund it? Well, 60% of the time you make money, 40% of the time you're not. You're going to lose money. And in fact, about a quarter of the time, you're going to lose about $1 million. That might be too much for your company to do. And so the expectation value being positive doesn't say necessarily that you should go ahead and do it, because the costs might, the costs are very high that if you lose that $1 million, maybe you go out of business or something. So expectation value for people who are doing business is a very useful number to know about what you're doing, but it doesn't tell you everything. You have to take into account a lot of other things to figure out how that works. And so that's the expectation value, and that's the end of chapter 8, which is